Hello everyone, my name is Thahat Bunsa and today I'll be presenting our computer vision project in the topic of virtual object placement using OpenCV. So let me start off by introducing my group member. Our group name is ถ้ามีสาวแว่นตัวเล็กน่ารักเทสดีสักคนก็คงจะดี So we have four members. Start off is Pachara Kimpa, second is Prashya Papapan, third is Purin Vinyapon, and the fourth is me, Thanapat Bunsa. Okay, let's talk about our concepts on our project. So in this project, we use AUCO markers to bring virtual 3D objects into the real world to augment reality, or people usually call them AR in short. So the system continuously analyzes a live camera feed to detect these markers and overlays 3D objects, either an OBJ or STL model, on top of the detected marker using OpenGL. So this makes it possible to visualize virtual objects as if they are exist in a real world space and aligning perfectly with the marker's position and orientation. To accomplish this, we rely on OpenCV for marker detection, but we did not use the built-in AUCO library from OpenCV. But we implement a manual detection system that extracts the marker feature from the image. But from this detection process, we obtain two important transformation parameters, such as the rotation vector or RVEC and the translation vector, or we could call them TVEC. With these values, it allows us to determine the exact position and orientation of the marker in 3D space, giving us the necessary data to correctly place a virtual object on top of it. So once we get all the transformation data, we pass it to OpenGL and which is responsible to rendering the 3D object. With OpenGL, it takes this information and then apply it to the object, ensuring that it is correctly positioned, rotated, and scaled relative to the real world marker. So in this way, when the marker moves, the 3D objects move along with it, maintaining its alignment and then creating the illusion that the virtual model is physically present in the real world. With this technique is widely used as an AR applications with including a product visualizations, interactive simulations, and industrial designs, where virtual models need to be superimposed onto the real world environment. By integrating computer vision with 3D rendering, this project demonstrates how digital objects can seamlessly blend into physical spaces, opening possibilities for innovative AR experience. Okay. So we move on to the next topic is why we choose this project. So the first thing is the topic is the real world application. So with this project, it allows us to verify the real world dimensions of CAD objects by overlaying its 3D model into physical reference using augmented reality by placing the virtual model on the Arduino Maker. We can ensure the object is correct scale and fits properly before manufacturing or assembly. So with this method, it reduces the need of physical before both time and resource. It has practical applications in industries like engineering, product design, and manufacturing. Next is the learning opportunity. So beyond its practical applications, this project serves as an excellent learning opportunity for a student exploring a key computer vision concept. It involves capturing image and detecting key features. So estimating the object positions and displaying 3D model in real time. Through this process, we gain some of a hand-on experience in working with OpenCV, OpenGL, and 3D rendering techniques. These are quite essential skills in the fields like augmented reality, robotics, and automation. So making this project is a strong foundation to move on into a future advanced application. And then the last one is the curriculum alignment. So these projects align perfectly with our program. Why? As it heavily utilizes OpenCV for computer vision tasks, it provides practical application of the concept we learned, bridging the gap between the theory and real implementation. And by applying computer vision techniques in augmented reality scenario, we strengthened our understanding of image processing, pose estimation, and 3D visualizations. More importantly, it enhances our problem solving abilities by allowing us to develop a functional system that integrates multiple robotics projects. Okay. So what are UCO makers? So AUCO markers uh, are special black and white square patterns designed for computer vision applications. So they usually act like an QR code that a camera can detect and recognize. This marker help to determine the object's positions, orientation, and the size in 3D space, from what I said before. So making them useful in augmented reality, robotics, and 3D tracking. So how does it work? So I would say that each AUCO marker has a unique grid structure, as you can see in the picture. So uh, by saying a unique grid structure, it has a defined size, a specific ID. The size of the grid determines how much the data marker can hold. For example, you can see a 4 by 4 marker has a 4 by 4 grid of black and white cells. So the ID of the marker is assigned based on its unique pattern. Example of the marker types. There are different types of AUCO marker categorized by the grid size and the number and unique markers that they support. So some example includes the ICT 4 by 450. So it's a 4 by 4 grid with 50 different marker IDs, or the ICT 5 by 500. So 5 by 5 grid with 100 markers ID, or the ICT 7 by 7,000. So it's a 7 by 7 grid with 1,000 markers ID. So the larger the grid, the more unique markers can be generated. So making higher grid size is useful for more complex application. So a 4 by 4 marker with ID equals 0, which is it's a simple black and white pattern. A 4 by 4 marker with ID equal 1, which has a different unique pattern. And a 7 by 7 marker with an ID equals 0, which has more squares, allowing for more unique IDs. So AUCO markers are useful and are quite powerful tools in computer vision, helping in applications to recognize and track objects in real world space. So the ability to provide precise position and orientation data make it essential for AR robotics and measurement applications.
So this is our OpenCV functions. As you see on left top, you can see this is our example crop image from these functions. Firstly, we going to conversion the gray BGR colors to gray because this can simplify the processing by reducing 3 channel to 1 channel, and this can benefit us to reduce computational play complexities and can emphasize the structural information. For mostly AUCO marker is already black and white colors. And next we are using the adaptive threshold to convert grayscale to binaries or black and white image. But why? Why we use adaptive threshold, right? Adaptive threshold can handles uneven lighting conditions all across the image. Our parameter is 19 and 2, which 19 is block size and 2 is constant for local thresholding. This can create clear distinction between marker patterns and papers. And next, we create the kernel 3 by 3. This apply to the morphology X. Morphology X is a noise reduction function. Our purpose is to remove small noise artifacts while preserving marker structure. And we use morph opens operation to erosion followed by dilation. And next, we find contour to shape detection of the rectangular shape of our markers. Uh, but why external mode, right? As external mode only capture outer contours of objects, which means that this can detect the rectangular objects. And next, this is our pure implemented flowchart of this AUCO detector from AUCO OpenCV. First, the three first is the pre-processing part. and the last three is the processing part. All I said before is the pre-processing part. We processing by validate the marker candidates is it have two or three markers or four markers, and then we solve the PNP for post estimation for the axis, and then we calculate the central post for central the modeling. And next, this is our detection process. First, this is just like you can see that is the frame provided, so we're gonna open camera or not. So if the let's say the frame already provided, and yes, next we are resize the frame to 1008 280 times by 70 720. We also create the display frame for debugging, but mostly with debugging is for the testing process, and then we convert frame to grayscale as I said, and three or three or four step next is all as I said before, and next is the process the control for marker detection. This is I'm going to show next like how they process the control detection, and then if the marker is detected, right, uh, we're going to return further. If returning further, they're gonna go into the next uh, post calibration or stabilization or Kalman filter next slide that I want to speak. Here you can see, first we app captures the frame from camera or users. This is provided frame any camera user one, and then we resize the frame to this frame we want, and then we convert the frame to grayscale for simplification as I said. You can see after we convert to grayscale and then we apply adaptive thresholding, you can see that we can exactly clear this thing between the markers and the papers, because binary image is just 1 or 0, and then we apply morphological opening to smooth the image. This can reducing noise. You can see that they have some noise on papers and then the noise is gone. And the last step, contour detection. As you can see, it can detect the all the marker outlined to identify the all the markers on the background of papers. And then this is I already speak about this pre-process. As I said, we going to firstly convert this to grayscale. No, sorry, we will just resize first, and then we convert to grayscale, and then we apply the adaptive threshold. Then we're going to morphological opening to reduce noise, and then fine contours for our markers outline. And then, but how we going to stabilize the post, right? After we fine contour, and then we post estimation by solve PNP for post estimation, there is some like unstable occurs when we solve the PNP. The z-axis is not is unstable at all for when we are acquiring our TVEC from the solve PNP. But we think that we can also use the Kalman filter to solve this from control theory that we learned from last semester, to filtering the AVEC TVEC for better approaching. So this is our flow chart. As you can see, if we are going to using Kalman, it should not be first detection. If it's first detection, it will be going to store as a data for baseline. Let's say this is not first detection. You can see that we going to apply Kalman filter if it's, and then we after we apply Kalman filter, due to we have a lot of data, right? Apply Kalman filter can approaching the base RX value for our post estimation, so that we can stabilize the z axis from RX because we can approach the base value for the RX, and then we convert to Coordinate and interpole rotation, and then we mark on the markers. And here is just OpenCV part. Thank you.
So, moving on to OpenGL. OpenGL is
powerful API used for rendering both 2D and 3D graphics. It provides an efficient way for software applications to draw complex objects on the screen, making it ideal for real-time rendering in graphics-heavy applications. Now, how is OpenGL used in this project? In our project, OpenGL is responsible for rendering 3D models onto detected Aruko markers in real time. It does this by using the rotation and translation vectors obtained from OpenCV's marker detection system. These vectors allow us to accurately position, scale, and orient the virtual object so that it appears to be attached to the marker in the physical world. Now, why OpenGL? OpenGL is crucial for this project because it enables fast and efficient rendering of 3D objects, ensuring smooth performance. It also seamlessly integrates with OpenCV, allowing us to overlay graphics onto live camera feeds. Without OpenGL, rendering 3D objects would be much more computationally expensive, leading to slower performance and lag. Now, about the process of OpenGL. First, it will be about converting the RVEC and TVEC into a transformation matrix. When an Aruko marker is detected, OpenCV provides a rotational and translation vector, which define the marker's position and orientation in 3D space. These vectors are converted into a transformation matrix, which is then passed to OpenGL. This matrix ensures that the virtual 3D model aligns correctly with the detected marker. Secondly, adjusting the object's origin point. By default, the 3D model has an origin point at 0, 0, 0. However, we need to align it with the marker. That's where the transformation matrix comes in. It moves the object's origin to the marker's position, ensuring that the model appears naturally attached to the physical marker when viewed through the camera. And lastly, OpenGL helps in rendering the object at the correct position. Instead of rendering the object directly onto the main frame, we first render it into a frame buffer object, or an FBO. This technique allows us to handle the rendering off-screen. The final rendered image is then blended onto the main OpenCV frame, ensuring smooth integration with the real-world camera feed. Now here is the main operation flowchart. First, when you start the application, the app will initialize OpenCV camera feed and the OpenGL. Then, OpenCV will try to detect for Aruko markers. If the marker is detected, the object will be displayed onto the camera feed, and then the OpenCV will try to detect the marker again. But if the marker isn't detected, the camera feed will only show the normal camera feed frame instead, without the object. Now for the flowchart of displaying the object onto the camera feed frame if the Aruko marker is detected. Firstly, it will create an FBO, or a frame buffer object. Then it will then get the transformation matrix from the rotation vector and the translation vector. Then the program will try to extract, load, and render the object using the given transformation matrix within the frame buffer object. Lastly, when the lastly, it will try to blend the extracted object into the camera feed and then display that blended frame. Now here's the flowchart of changing from the rotational vector and the translation vector into the transformation vector. Firstly, when there's an input of the rotational vector and the translation vector, the rotation vector will first transform its shape from 3 by 1 into a 3 by 3 rotational matrix. Then, the rotational matrix and the translation matrix will be combined into the transformation matrix with the shape 4 by 4. Then, so that the dimensions of OpenCV matches the OpenGL dimensions. The y-axis and the z-axis is flipped. Lastly, the transformation matrix will be transposed and then outputs. And here is the flowchart of rendering the object. Firstly, the frame buffer object will be binded into the frame buffer, and then all the setup of the camera will be set up like the FOV. Then the previously used transformation matrix will be reset. After that, the model will be drawn on the marker using the given transformation matrix. Next, it will extract the object from OpenGL so that it only gets the object and not the background, and then unbind the frame buffer object from the frame buffer, and then output that object to be used in the camera feed. And here are the results of the application. Now, for our future work, while this project successfully renders 3D models onto the Aruko Marker, there are several areas for improvement. Firstly, we should support for more 3D files formats. Currently, it only supports an OBJ and STL model, but for future work, we could extend that into additional CAD formats, which would allow the user to load various industry standard files. Secondly, we can enhance the user experience, making the system more interactive and improve more by adding UI controls, and user could maybe scale, rotate, and reposition the 3D object within the AR view. And lastly, we could also improve it by giving it a mobile AR integration, which to make which is to make the project more portable. It can be integrated into a mobile device using AR Core for Android and ARKit for iOS. These frameworks provide powerful tracking capabilities and marker-based and markerless AR features, which would allow the application and allow the objects to be placed in real-world environments without the need of Aruko markers. Thank you.